Okay, we're going to finish the Ax-Grothendieck theorem today, which is very exciting. So we need to finish off the Lowenheim-Skolem theorem. Last time we finished proving the lower Lowenheim-Skolem theorem, which is definitely the more difficult one. So there is an upper Lowenheim-Skolem theorem, and this is very, very simple to prove. So let I be a model of some first order theory T, and assume that this has infinite cardinality. I can say is infinite. So A is my one and only sort of the first order theory T. That's just the same theme that I've been using throughout these lectures, that we're only considering theories with the single sort here, and I've been calling it A. Okay, and then the statement is that for any cardinality greater than the cardinality of the set I of A, there also exists a model J of T of that cardinality. It's a T, that's not I. Such that the magnitude of J of A is equal to kappa, okay? And the proof crucially uses the compactness theorem. So all that we do is we fix a particular set of cardinality kappa, any set whatsoever. So let X be such a set. Okay, and then for each X inside X, we construct a constant symbol. So we parameterize a collection of constants by X. Okay, and then what I do is I define the following set of first order formulas. So I'm going to let squiggly X be the set of the following sentences, which is just, it's not the case that Cx is equal to Cy, given that X and Y are non-equal elements of X. Right? So it's the dodgiest thing that you can possibly imagine. So what I'm going to do is I'm going to consider any finite subset of X and then prove that we have a model of the theory T extended by this finite subset. And all I do is I take the model I of A and then I interpret all of the CXs that come up inside my finite subset of X, of which there are finitely many of them, as distinct elements inside I of A. Since I of A is an infinite set, this is always possible. And then by the compactness theorem, this implies that there exists a model of the union of all of these theories, which is T, and join all of these constant symbols, right? And then I can construct a model for the original T, which is just going to be the model for T extended to all of these constants, because I just throw away the constants and I don't use them. Now, the point is I have kappa many constants, and so I definitely end up with a model of size at least kappa, right? And then I use the lower Lowenheim-Skolem theorem to reduce this down to exactly kappa. So let squiggly X prime be a finite subset of squiggly X, then let C sub squiggly X be the constants appearing in the sentences or the formulas of squiggly x prime. I'm on the second board now. Then the theory T sub C x prime, which is the theory T extended to the constants C x prime, has a model. What I do is I take I and interpret each, let's say C, an element of Cx prime, as some element of I of A with all choices distinct. This is possible as squiggly x is finite and I of A is infinite. Cool. So it follows from the compactness theorem that T sub C, the theory with all the extra constants, has a model. Let's call that K. Okay, and the point is that K has an interpretation for each of the constants and they're all distinct elements. And so therefore the magnitude of K of A is at least kappa. And moreover, it is clear that kappa is a model of T, the original theory that we considered. So lastly, we apply the lower, this greater than is greater than or equal to. So it might be of cardinality kappa on the nose, but if so, that's a coincidence. But if it's greater than it, no problem. We just, pardon? Oh, did someone say something? Oh, I think that was actually my own voice echoing in my ears for some reason. Okay, apply the lower. Yeah, definitely not. And some meta theory disagreement happening inside my own brain. Okay, apply the lower Lowenheim-Skolem theorem to equals kappa. Good, and that's a proof. Okay, is that simple enough?
I'm still trying to follow just the, I guess, first half of the argument. So the set X of just stuff, this is just something that we make new constant symbols out. It's not, is it related to any of the, to the original model I at all, or is it, it's just some set?
No. So I need to assume the existence of some set of cardinality kappa, right? And
yeah, okay.
Yeah, and so I can just use the elements of X as the constant symbols themselves but for pedagogical reasons, I decided to make constants out of them. But I was trying to emphasize the fact that it totally doesn't matter. X is just some completely random set as long as it has cardinality kappa.
Okay, hang on. So then the constants cx and cy and so on, they don't occur anywhere in the theory T. They're completely new constants.
Yeah.
So you can just consistently add all these sentences.
Yeah.
As you please. What's the argument for saying like I'm just trying to follow why you don't just say like why isn't it obvious that the whole thing has a model?
Because the cardinality of X might be bigger than the cardinality of I of A, right? Now, in that situation, I'm not going to be able to pick distinct elements inside I of A in order to model the constants. And so in that circumstance, I can't have a model of this extended theory because there will be some pair of constants that get mapped to the same thing.
Yeah, okay. Okay, so but you can always do it when you just take finite subsets of X, because then you only have to pick finitely many distinct things.
Yeah, okay. Exactly. Nice. Cool.
That's like pretty crazy.
Yeah.
Like, what is your reaction to this? That like, I guess is it just saying that you can like take a like the model and the sentences in the original theory isn't really completely isolated from all this like extra garbage, because it's still, when you have like universal quantifiers, like they have to like still be true, so they have to still say something, or like they have to hold of all of this extra garbage that you've thrown into the domain.
Yeah, but the extra garbage that I've thrown in is completely disjoint, right? So what we're thinking about is, so
like, yeah, it's like a different like you've
it is because I haven't added elements to I of A, so I'm only considering finite collections of the constants at any particular time. And so the elements that I pick are genuine elements of I of A. I don't extend I of A until I appeal to the compactness theorem. And at that point, there's a lot involved in that maneuver, right? So I'm using the compactness theorem, and you prove the compactness theorem using the completeness theorem, right? So there is some crazy process that gets applied to I of A and all of its finite submodels that then produces some unwieldy big thing. And I don't feel like I have, off the top of my head, knowledge of that. I just believe that there is some process that we've a priori discussed. And the result of it is some model which has to be consistent. And so there has to be at least kappa many distinct elements inside it. And so therefore it must have cardinality at least kappa, right? So it's a hands-off proof. It's an indirect argument.
About that last step that you just described, like the logical step from knowing that every one of these sentences of squiggly X is true in the model, to like to knowing the size of the model K.
So
what's the like how do you determine whether like a set has a certain size? Like usually you form like a bijection or something, right?
So there's an injection. There's an injection from X into the model that I end up with, because CX is interpreted as some element. It's provably not equal to any of the other elements of the form C sub Y, where X is not equal to Y, right? And so that element, that Cx, gets interpreted as map X inside capital X to that element, right?
Yeah.
That's an injective map from X to this set. And so therefore this set has cardinality at least that of X, which means it has cardinality at least kappa.
Yeah, okay. That seems pretty reasonable.
Yeah. Okay, let's move on. So now we get the Wash-Vort test, which is spelled with an L.
Stupid comment, but every time I hear this, I think of the test in Blade Runner.
I haven't seen Blade Runner.
Okay. It's the test for whether you're a replicant or not, whether you're a real human.
Oh, I see.
It sounds sort of
Starting
similar.
to. I think it's going to sound more similar as I write out the lemma. Okay, let T be some first order theory. Over some first order signature sigma, and I'm not assuming that it has one sort at this exact point in time, but that's going to be literally my first dot point. So assume sigma has only one sort. This lemma holds in more generality than this, but this is the only one that we've proven, and this is the only one that we need for the Ax-Grothendieck theorem, so it's fine. Sim T has no finite models. Okay, and assume that there exists some cardinality kappa, which is necessarily infinite due to dot point 2. For which there is exactly one model up to isomorphism of T of size kappa. Okay, and so the example that we want to have in our heads obviously are algebraically closed fields. Okay, so to the geometers in the room, it's standard theory that there are no finite algebraically closed fields, and for any cardinality, there is exactly one algebraically closed field of that cardinality up to isomorphism when you pick a particular characteristic as well. So that's the motivating example from our perspective, but this is a general test that holds. And what it says is that if this holds, then T is complete. Okay, and again, the proof is simple, but it seems a lot less hacky than normal, so that's good. So the proof. So
you said one model up to isomorphism. Like we didn't really define like model isomorphism, but you just mean like is it just the size of the set or?
It's not necessarily the size of the set. It's so you need to talk about morphisms of what? Models or theories? So I suppose the pause is, I'm going through my notes. I think I actually had this at some point. Yeah, so there are morphisms of interpretations. Yeah, so you have a fixed first order theory, and then you might have two different interpretations of it, and there is such thing as a morphism from these interpretations, and it's obvious what it is. So I need a function from the domain of the first interpretation to the domain of the second interpretation, and I need these to be coherent with the interpretations of the function symbols and the interpretations of the predicates or the relation symbols. And if you have a reverse map, or an inverse map, then you have an isomorphism. So in the example of algebraically closed fields, that's going to be a field isomorphism.
Yeah.
Cool. Okay. Now, if we assume that T is not complete, then by the completeness theorem, we actually have a pair of models in our hands, one of which models a particular sentence and the other model models the negation of that sentence. Phi, a formula such that I models phi and J models the negation of phi for some models I and J. Okay, and then we're done because we know that we have no finite models, right? And so what that means is that I and J are both infinite, and then we can use the Lowenheim-Skolem theorem. So I and J are both infinite of some cardinalities, kappa 1 and kappa 2, say, but whatever they are, I can come up with a new model of, there exists, oh wait, how do I get the preservation? Oh, I see, okay. Okay, let me move to the other board to make this precise. I think it's confusing because I'm saying it out loud. So let's move over to the next board. Okay, so I and J are both infinite. So by Lowenheim-Skolem, there exists a model K of T such that K models phi and K models the negation of phi, which is a contradiction, right? So the way that you want to think about this is I of A might have some cardinality kappa 1, and then the magnitude of J of A might be equal to kappa 2, say. Then if kappa 1 and kappa 2 are equal in cardinality, then you're already done, right? Because we only have one model up to isomorphism for a particular, I guess we need to, okay, so the assumption in the hypothesis was that there exists some kappa for which there is exactly one model of T of size kappa up to isomorphism. So I actually have a kappa sitting around. So yeah, this isn't quite correct what I've written on the board. So that, yeah, no, that is fine. Just ignore that sentence. Such that this holds and the magnitude of K of A is equal to kappa, right? This is because there is only one model of size kappa up to isomorphism. Okay, and where we used the Lowenheim-Skolem theorem is in the construction of the model K. Does that make sense? So that's a contradiction. So T is complete. Okay, so the next step is to show that the first order theories of algebraically closed fields of either characteristic 0 or P, where P is some prime, satisfy the criteria inside the Wash-Vort test. So before I jump over to algebraic stuff, are there any questions on this proof? Okay. So, lemma. If K is algebraically closed, then K is infinite in cardinality. And this is a really slick argument. It's one of those very simple but nice ideas. So say K is finite, then consider the following polynomial. So I set f of x to be 1 minus the product over all alpha in elements in kappa of x minus alpha. This is an element of this polynomial ring, right? And if I evaluate f at any alpha inside k, then we can see that I get the value 1, which is not equal to 0. And so therefore, k is not algebraically closed.
Nice.
Yeah, it's nice, isn't it? Okay, and so that's the second dot point of the Wash-Vort test, telling us that there are no finite models of these algebraically closed fields. Sorry, no finite models of the algebraically closed theories, which is just the algebraically closed fields. Okay.
I reckon this theorem also kind of like is also saying that like there's no way to sort of come up with an idea of a product over like infinitely many elements of a field, because then you could sort of like violate this theorem.
I don't know if this. Oh, by this theorem, do you just mean the lemma that I just did?
The lemma, yeah.
Yeah.
As in, like, you can't define something with infinitely many inputs that sort of behaves like a product would, in that if one of the things is 0, then the whole thing is 0 or something.
Yeah, I don't know if that's like, the thing is, the finiteness assumption of polynomials and of products inside groups and algebras, etc. I mean, they're certainly motivated by more than just the fact that you can't. There are notions of infinite products and infinite sums out there, but we're considering structures that don't do that. So
right.
I'm not sure.
So I guess the idea of algebraically closed has the finiteness baked into it. Like, it's a question about
because it's a question about polynomials. Yeah.
Yeah.
Okay.
Just a thought.
Yeah. So now we're very close. I just need to prove that there is only one model of each infinite cardinality for algebraically closed fields. For this, I just need to get my hands a little bit dirty with the canonical construction of an algebraically closed field from a non-algebraically closed field. So maybe let me just remind you that every field F can be embedded into an algebraically closed field. Hey, have I lost sound? Can you still hear me?
Yes, I can hear you.
Okay, good. So my headphones sounded strange, and I was worried that I lost you. Okay. F can be embedded into an algebraically closed field. We normally just call that F bar. And the construction is like this. So for every monic irreducible f inside f of x, we introduce formal indeterminates, necessarily finitely many of them. So u sub f dot 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 u sub f d, where the degree of f equals d, right? So for each monic irreducible polynomial, I introduce d plus 1. Is it d plus 1? Yeah, d plus 1 indeterminates, where d is the degree of f. And then I define this new
U0, like
U
subscript.
F0, yeah. So each U has a pair of subscripts, U sub F0 up to U sub FD.
And what are they? They're just variables or what?
Formal symbols, yeah. These are going to be indeterminants inside of the polynomial ring that I'm just about to write down. So I'll let G be the polynomial ring over all of these indeterminants with base field F. And then the clever trick is you write F minus the product of all of these corresponding to F. So this is X minus U sub Fi. And
the set G equals F of this set of formal symbols. Is that set also like ranging over all F, or is it this is fixed F?
It's ranging over all F.
Okay. And then now you're below here, you're fixing F again? Or?
Yeah.
Yeah, okay.
Okay, so then for each of these monic irreducible polynomials, I take F minus this product and I expand that out, right? And I'm going to end up with some sum that looks like this, where I have alpha sub Fi multiplied by x to the I, and this is an element of G as the base ring in a polynomial ring, right? So we work inside this polynomial ring. I can construct this polynomial and I just do the massive expansion of the big product and simplify everything. And I end up with some polynomial over x with coefficients inside G. And then I take all of those coefficients, alpha, Fi, and I mod out by all of those. And so you can see what I'm doing is I'm forcing this difference of polynomials to be 0, which means I've introduced a factorization of f, which wasn't there earlier, right? So I'm constructing an algebraically closed field. Okay, so the point is the ideal I generated by all alpha Fi is not all of G. So it's contained in a maximal ideal, and that's using Zorn's lemma. So I've just used ZFC. I've used choice in ZFC. I'm trying to think if I'm using it in the meta theory or in the theory. I guess this is inside a model, so I'm using it inside ZFC. So that's fine. Okay, it's not all of G, so by Zorn's lemma, I is a subset of M with M maximal. Okay, I need to move to the next board. Okay, and so then what I do is I define F1 to be equal to G modded out by the maximal ideal n. Okay? And that is going to give me a new field because I've modded out by a maximal ideal. So that's a field. But I've introduced new indeterminates. So there might now be new monic irreducible polynomials inside F1. And I need algebraic closure. I need factorizations of those as well. Okay, so I need to repeat this process in order to define Fj for all j in elements of the natural numbers. To obtain for all j greater than 0, and then define F bar to be equal to the union of all j greater than 0 Fj. Okay, then F bar is algebraically closed. And F embeds into it. Okay, so that's the proof of the lemma. That's just the standard construction of the algebraic closure of a field. But the reason why I wrote it out again is because I need to look at this and observe that the cardinality of the algebraic closure of a field is uncountably infinite if the original field was finite, and it's of cardinality kappa if the original field is of cardinality kappa. So the crucial argument for that, I would really like to point to something that's on the previous board, that's a shame, whatever, is that I add indeterminates.
Why is it uncountable if f was finite?
Because I have introduced polynomials over a finite field. And as soon as you do that, you end up with an uncountable set. Can you see that? Because a polynomial could have arbitrary degree. And so all polynomials look like coefficient plus coefficient times x plus coefficient times x squared plus dot 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 plus coefficient times x to the n. And so I'm looking at the set of sequences of length n, where each element is an element of the finite field, and n is ranging over all natural numbers. That set is countably infinite. Whoa, did I say uncountably infinite? It's countably infinite. Oh, okay. Sorry, that was a slip of the tongue. It's countably infinite.
Okay. We were both sitting there like, that sounds countable to me.
Yeah, it's like we just gave you the most
telling me
mathematical proof of the. So pretty funny exercise to give a proof of the statement you're exactly trying not to, or you haven't stated. Okay, so yeah, sorry, it's countably infinite if f is finite. So that's the next corollary. F finite implies f bar is countably infinite. And the magnitude of f equaling kappa implies that the magnitude of f bar is also kappa. Okay, and it's the same argument for both of them. So you're taking polynomials over a field, and
this is for kappa at least countably infinite, right?
Yeah. Good. Okay. So now we can do the final lemma of the entire theorem. So lemma, let P be either prime or 0. Let kappa be greater than or equal to Aleph 1. I guess that's so stupid to say. Okay, let kappa be uncountable. Oh, how do I say that? I don't want to like assume continuum or something. Let kappa be the cardinality of the real numbers. Okay. Then actually I don't know how to do that. Okay, sorry, the statement's a bit awkward because I don't want to like get into Aleph1 and Aleph0 and stuff, but I can say let kappa be greater than Aleph null, and I'll leave it there. Okay. And the statement is there exists exactly one algebraically closed field of characteristic P whose cardinality is kappa up to isomorphism.
This is the premise of the Wash-Vort test.
Exactly. Yeah. So this is dot point 3. Okay, the proof. So first I'll take a particular choice of base field. So I'm going to define it to be the rational numbers if P is equal to 0, and the field with P elements, a finite field of characteristic P if P is not equal to 0, and then let S, this is kind of hacky again. This is actually a very similar argument to what I did in the proof of the Wash-Vort test. So I'm going to introduce a collection of indeterminants parameterized by a set of cardinality kappa, right? And then I'm going to take the field of fractions of the polynomial ring in those indeterminants over the field F, and then take the algebraic closure of that. So that's the existence, and then uniqueness follows from the universal property of algebraic closure. So it's a pretty simple and a little bit hacky argument. So let S be any set of cardinality kappa, and consider the field G, which is F brace, not the square bracket, X, S, given S is an element of S. Okay, and that's just the field of fractions of this polynomial ring, if you're a bit squirmish about the existence of the field that I just wrote down. Okay. Then from the previous corollary, G has cardinality. Oh, sorry. No. Not from the previous corollary, but just by observation, G has cardinality kappa because of the indeterminants. And then, so by the previous corollary, the algebraic closure of G also does. Okay. And as I already said,
could you remind me why the algebraic closure isn't bigger?
Because we are taking, hold on. So it's clear in the case where, no. So the reason why it doesn't have greater cardinality is because the the polynomials over a field are parameterized. So a polynomial over a field looks like this. We're looking at the set of all things alpha naught plus dot 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 plus alpha n x to the n, right? Given alpha I are an element of f, okay? And then as a set, that's in bijection with all of the sequences alpha naught up to alpha n, given alpha I is an element of n, of f, and n is greater than or equal to 0, right? And so this is the set of all sequences. It's a countable union, j equals 0 up to infinity of the set of sequences of elements inside f, right? And so the cardinality of that is equal to the cardinality of the elements inside f, presuming that f was infinite a priori, whereas if f was finite, then this bumps it up to countably infinite.
Yeah. Right. So that's the polynomials over the field, but then the algebraic closure involved like modding out a bit, right?
So the modding out. So are you worried about the modding out reducing the size of the algebraic closure?
Yeah, but you said something about f embeds into it.
Yeah, f embeds into it because we only ever modded out by informal indeterminants that we added in, right?
Right, yeah.
So the coefficients are still there, so f embeds into it.
Yep.
Cool. Okay, so, but I need to be careful here. In the case where P is prime, then Fp is finite cardinality, which means the bottom statement is wrong. So G has, yeah, let's, no, this is correct. Okay, so I haven't used the size of F here. Because F, be it a field, a finite field, or Q, I still adjoin kappa many indeterminants, and so therefore G definitely has cardinality kappa, so we're fine. Okay, and now what I need to do is take a transcendental basis of G, I believe. Yeah, so if I take any transcendental basis A of G, and to remind you what that means, it simply means that G is equal to the polynomial field over those elements A, right? So that's the same notation as beforehand. Take the polynomial ring with base field K over these elements A, and then take the field of fractions. If that thing is isomorphic to the original field that you started off with, and since it's a subfield, it's equal on the nose. If that is the case, then A is called a transcendental basis of G. And we observe that A has to have cardinality kappa. And again, it's the same argument that we've been using. G is equal to all of the polynomials over A. And so the set that we started off with, if that was finite or countable, then polynomials over that would be countable. But we know that kappa is greater than that. So therefore, A has got cardinality kappa. Okay, moving on to the next board. Now, if I let H be some other,
you got to move your character.
I'll do it. Oh yeah, sorry, I forgot which. Okay, if H was any other algebraically closed field of characteristic P, then I can do the same trick. There is also a transcendental basis of H, which has cardinality kappa. What did I call it? I called it A. Yeah, so B of H with cardinality kappa. So, therefore, there exists a bijection between A and B. And that induces an isomorphism between the polynomial field over A and the polynomial field over K. So again, I think I misspoke. So this induces an isomorphism between the polynomial field with base field K over A and the same such thing, but over B. And then don't forget that by hypothesis, that one's equal to H and this one's equal to G, right? Okay, and now we just take the algebraic closure of both sides, and since we have an isomorphism of the base fields, that induces an isomorphism on the algebraic closures. So we have J bar is isomorphic to K of A bar is isomorphic to K of B bar is isomorphic to H bar. So therefore, J bar is isomorphic to H bar. Cool, and that's it. And so now we can see that the first order theories of algebraically closed fields of characteristic P, where P is either prime or zero, satisfy the conditions of the Wash-Vort test. And so therefore, these are both complete theories. And that was the only remaining assumption that I made in the first half of the proof, which I've already done. So that completes the proof of the Ax-Grothendieck theorem. Woo. Yeah. Any questions on the last bit?
The conclusion of this is that the algebraic closure of G and of H are isomorphic.
Yeah.
But weren't G and H the algebraically closed fields of characteristic P? Didn't we want to show that G and H were isomorphic?
Oh, that's a good point. I mean, I have that anyway. So wait, what am I trying to say? Oh, I think I don't need a bar here. Yeah, okay, good. So J was not an algebraic. Yes, because, hold up. Yeah, there is something wrong here. So that's a subset. Okay, sorry. I made some mistakes here. I don't know, I must be tired today or something. Okay, I have taken a transcendental basis for H. So this, interesting. So no, the equalities are true, but the last one's trivial, right? So I take the algebraic closure of H, but that's isomorphic to H. Because H was algebraically closed to begin with. But G wasn't, right? G was some field that I constructed, and then I took its algebraic closure, and then I said that that thing is unique. And how do I prove that? I assume that I have some other thing, which is H, which is algebraically closed, so there's no bar. And then I prove that there's an isomorphism between them.
And sorry, could you go over the first part of the story? Like you started with F. What's the role of F? And Why do we start with f and then
The reason why f
why
disappears.
don't we fix shouldn't we be fixing an arbitrary G, which is an algebraically closed field of characteristic P, not like this particular one constructed from F?
So the point is, no matter what G you pick, F is a subfield of it. So you can just take the element 1 inside your field and then consider 1 plus 1 and 1 plus 1 plus 1 and 1 plus 1 plus 1 plus 1 dot dot dot. And that gives you a subset, which in fact is a subring, which in fact is a subfield, right? And so those subfields are either Q or FP, as I've written here. So yeah, the statement is about arbitrary G, but the point is any arbitrary G will have F as a subfield, and that's where I started.
Mm-hmm. And then what properties of F did you use?
Cardinality properties. So I quickly kind of mod it out by the difference between P equals 0 and P not equal to 0 by adjoining all of these different indeterminates, right? And once I've done that, BF finite or uncountable, this thing now has cardinality kappa, right? So that's a property of F, but not a very deep one. And then I just worked with G from then onwards because I had a grip on it. Okay.
Cool.
All right, are there floating trees again? Looks like it. Cool.
Yeah.
All right.
There's a tree hiding behind that last board.
It's just listening.
Right.
Relax. It's interested.
Okay. Yeah, I've got nothing to be scared of. I'm sure.
It's actually stuck. Oh no, it's not. Anyway, you are not its prey tonight. Someone.
All right, good.
You trying to trap me?
Well, no.
I'm about to give my class for category theory here now, so
thanks.
I better head off. But I've got another minute. Are there any final questions, or are we done?
No, I don't have a question. Thanks, Will. That was good.
Yeah, no sweat.
Thanks. Did you have any other concluding thoughts about?
Yeah, I've got a lot of concluding thoughts, but I want to write them out kind of properly. So I won't say them here, and I'll save them from the recording, and I don't know, post them on the channel or something.
Cool.
Right. Okay, I'm gonna head off. Thanks, guys.
Yeah.
I'll see you soon.
All right. See you, Will. Thanks.
Get lost. How come you got the respawn halo? Did you reset your character and then? No, you can't have. How did you get that?
No, I hit the return button on the orb thing.
Yeah, I know, but why did you get you had the halo around you as though you just spawned in?
Oh, because I died. You like yeeted.
Oh, I did. Okay.
Okay.
You just reacted and smoothly continued, so I didn't even notice my success. So rude.